Okay, so this is the fourth video in our work and energy module. We're going to start off with a little discussion on conservative forces and potential energy. We're going to see that the potential gravitational energy that we defined in the last video um, is actually definable because the gravitational force is a conservative force. Okay, so conservative force is one which is like the gravitational force, for which the work done against it depends only on the work done by it or against it depends only on the starting and ending positions of the motion, right? So it's not path dependent, and any conservative force can have a potential energy defined for it, just as we did for the potential gravitational energy, right? And so if we think back to the last video, remember we had this little drawing where we had some height like this, and we had another height, which is basically the same height, where we took so in the first case we took this direct path, in the second case we take this crazy curly path, and we find that in the end we have the same potential gravitational energy stored in the system, regardless of how we sort of made this trip, right? Both of these resulted in the same potential gravitational energy. Okay, and that's just telling us that our gravitational force is a conservative force. Give me 1 second here. Having slight technical difficulties. Well, in any case. Okay, anyway. Okay, so the key points to remember are that the potential energy of a system is due to the position, shape, or configuration. So we saw that that in the case of potential gravitational energy, we talked about how the energy is not actually stored in, say for example, we're lifting some sort of a brick. The energy is not actually stored in that brick. It's stored in the system formed by the brick and the earth, right? We're now going to take a look at a situation where we have spring potential energy, and the energy is stored in the configuration of the spring, right? So if we had some spring that was not compressed starting off, and we compress the spring down, and we have this much compression here, this is supposed to be the same spring. The energy is stored in the fact that we've changed the configuration of this spring. We've pushed the spring down, and now we have some potential energy stored in that spring. Okay, but we're going to take a look at that in a second. Let's take a look at a few of these other points that I wanted to remember as sort of key points here. So potential energy is energy that's stored, that's completely recoverable, at least in principle. So it's not energy that's sort of lost to us. In the case of gravitational potential energy, we can tie some sort of generator or something to this brick that we've lifted up, and we can now extract the energy that we have stored in the system. Our third point here is that a conservative force is one for which the work done by or against it is path independent, and we just talked about that in the case of gravity. And then finally, the last point is that we can define a potential energy for any conservative force. Okay, so these are just useful sort of little points to remember about the way that potential energy and conservative forces relate to each other. So now we're going to take a look at spring potential energy. It's just another type of potential energy that we're going to find it useful to work with. And so we start off from Hooke's law. So we should all recognize Hooke's law here. And we start from Hooke's law. Let's remember what Hooke's law is telling us. It's telling us that the force needed to compress or deform a spring is equal to its spring constant times the amount that we're deforming it, right? And remember from the last videos on when we were talking about Hooke's law, we talked about how this is for how this deformation follows a linear law, right? That's why Hooke's law works. Like we have this linear section, and then we have other stuff happening where we have our our brake and stuff. This is all from previous videos, so maybe I shouldn't be drawing this here, but you can all look back at the previous video series and see where Hooke's law comes from. But basically, we can argue that because this x is increasing linearly, that the average force needed over this deformation of x is going to be somewhere in between 0 and kx, and in fact it'll be right in the middle of 0 and kx because we have a linear region, so the force required there is going to be exactly a half kx, and so that's what we've argued over here. So we say that the average force for this deformation, well, the average force needed to generate this deformation is going to be a half kx. Then the work done in deforming the spring will be given by the formula that we have here. So we have the work done against the spring here to deform it is going to be equal to F times the displacement that we have. But again, if we think about the spring and we think about deforming it in this way, we're applying a force in this direction, but we also have the deformation in that direction. So our cos theta ends up being a cos of 0, which just gives us 1, which is why we don't have a cos in here, okay? But so we can then replace the force, like we just talked about, from over here, the average force that we're going to need over that deformation, and we end up with the expression that we have here, except that this deformation ends up being x, right? We're deforming this some distance x, and so we can just replace this d with an x, and we end up with an x squared, and we end up with the expression that we see here, right? And that's great. We define this work that we've done on the spring, storing this potential energy in the spring, as the spring's potential energy, and this is our expression for our spring potential energy. I probably should have boxed this one, so I'll box it. This is going to be our definition for a spring potential energy, 1/2 kx squared, and we're going to use that sort of going forward here. Okay, so let's change gears a little bit here. We're going to go back to the work energy theorem, which we talked about a couple of videos ago. And the work energy theorem tells us again that the net work done by all forces acting on a system is equal to the change in the system's kinetic energy, right? And we saw this earlier. This is an equation that we kind of derived and then saw earlier and worked with. But now we're going to consider only conservative forces doing work. And so this is simple enough. Our net work becomes just this work done by conservative forces, so nothing too fancy going on over there. And then if we drop these terms in the center, we can write the equation that we see here. Okay, so that should be fairly straightforward. If conservative forces do the work, the system then loses the potential energy stored in it, right? Because these conservative forces are changing this potential energy into kinetic energy, and we argued this in the last video in the problem that we did, that all the potential energy lost by that person falling was being turned into kinetic energy as they were approaching the ground, right? And so this is the same idea. We're just restating it again here, that all the potential energy lost by work done by these conservative forces is transferred into kinetic energy in the system. Okay, and so let's start off from this point, and let's manipulate this equation a little bit. So we see it down here, and so I just move the potential energy over to the other side, and then kind of rearrange it, right? So we have the change in kinetic energy plus the change in potential energy is equal to 0. Which is not surprising given the equation above here, right? And now we can break up this change in kinetic energy. So this is our change in kinetic energy broken up into final and initial kinetic energies, and this is our change in potential energy broken up into final and initial potential energies. And then I simply isolate the initial and final kinetic and potential energies on each side, right? So we end up with this equation that we see here. And when it's written in this way, this is a statement of conservation of mechanical energy. This is a sort of very important idea that we're going to work with here, and so I give it a box. And so what is this equation really telling us? Well, it's telling us that that where only conservative forces are acting, that the sum of our initial kinetic and potential energy has to be equal to the sum of our final kinetic and potential energy, I should say, right? And so we see it here. We're going to make use of this equation quite a bit, and I'm going to start off here with a sort of big example. It's going to take us a little while to dig through here. So I have some of the numbers worked out here on a piece of paper, so I'll be able to put those in as we do the calculation, if I can find it. Yeah, here we go. Okay, so let's start off by setting up the problem. So what do we have here? We have a 1 kilogram toy car, which is propelled by a compressed spring. The car runs around a track and ends 0.18 meters higher than it started, so 18 centimeters higher than it started. The spring is compressed 0.04 meters, so 4 centimeters, and has a force constant or spring constant of 250 newtons per meter. Assuming no friction, find the following. So in part A, we want to find how fast the car is going as it enters the track, so at point FA. And in part B, we want to see how fast the car is going at the end of the track, so at point FB. And here I mentioned that we're going to do some additional work for parts C and D, which is additional stuff that I've added on top of the example from the text. Just an interesting little sort of demonstration of how we would expect these things to work. So okay, let's jump in and sort of start off here. In part A, we're being asked, well, we can see here we have the spring, we have our car here, and the spring is compressed as the car is pushed up against it. So we want to start the whole thing. We want to release the car, let the spring release all of its potential energy into kinetic energy for the car. And we want to see how fast this car is going at the point FA here. So it's gonna accelerate, and at the point FA here, when it's like on the track over here, we want to see how fast it's going at point FA. Okay, so before we get into actually answering part A, B, and C, and so forth, I'm just going to set up a sort of very general equation that we're going to be able to use to solve all these parts. Okay, and so if we look back, we just talked about this conservation of mechanical energy. So I'm just going to write down that equation to start with, and then we're going to account for all the different types of energy we have here. So let's start off. We have kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final, right? And now we just need to be careful that we're accounting for all the energies that we need to be looking at in the system here, okay? And so kinetic energy initial, well, there certainly could be some initial kinetic energy, and we know that kinetic energy looks like this, half mv, and I'm going to call it half mv initial squared. And there can be some potential energy, but in this case, we have the I want to say the potential to have potential energy, but we have several potential sources of potential energy here. First we have gravitational potential energy that we could have. So we could have some mgh, right? So some initial height times our mass and gravitational acceleration. But we also, because we're dealing with a spring here, could have some initial spring potential energy, right? And we know we would write that like that, and I'm going to call this x our initial x is our initial spring compression, right? And so here we have all of our sources of kinetic energy. Here we have all of our initial sources of potential energy, and these need to be equal to the final energy, right? And so again, in the end, we may have some kinetic energy. We may have some potential gravitational energy. Excuse me. We may have some potential gravitational energy. We also may have some potential spring energy. And so again, we have our, so these were initial. We have our kinetic energy final here, and a couple of sources of potential energy final here. Okay. And so we're going to sort of use this this equation that I have laid out here as a sort of blueprint to solve all these parts of the problem. Okay. So let's start off in part A. And in part A, well, I'm just going to start off by copying down the equation that we have again. All right. Okay. And in part A, our final point is this final point FA, right? So I'm just going to change all the subscripts to FAs. Here you see I changed the F to an FA here. I'll do the same here. And I will do the same here. Okay? And so let's think about what types of energy we actually have. So initially the car is up against the spring. It's not moving. So we have no initial kinetic energy, right? So we can remove that term. We could have had some initial kinetic energy depending on what we count as our starting point, but in this case we didn't. So that one's gone. Do we have potential gravitational energy? Well, it kind of depends what we consider HI to be. But if we call HI our zero, like if we look up here on our drawing, if we set this as our y equals 0, and this h final as y equals h final equals 0.18 meters, then we're not going to have any change in our gravitational potential energy, right? We end off at HI here, and H final at FA is still HI, right? So really both of these terms are just going to end up canceling out. I'm going to draw them like this. These are just going to cancel out because we have the same height in the beginning and the end, right? So there's no change, so there is no gravitational potential energy changing into kinetic energy or anything else, and so we don't have to consider that. And the last thing that we can cancel here is this term. And we can cancel this term because, so in the beginning we have some spring potential energy, but after the spring releases the car and the car ends up at point FA, there's no more spring involved in the problem, right? And so there is no more spring potential energy stored up, and so we can get rid of this one as well. Okay. Excuse me. So that simplified a lot. We can now rewrite this equation in the form that we see here. We can cancel out these 1/2 factors. I'll rewrite it one more time. Okay, and what are we interested in? Well, we're interested in what the velocity of this car is at the point FA, and that's what this VFA is. So let's isolate VFA. If we're sort of careful about how we do that, I won't go through too many steps here. It's really just a couple of steps, but basically we end up with VFA is equal to, and I'm going to choose the positive root here. So we're going to end up with square root kxi squared over m. I guess we could pull out that xi squared, so we would just end up with k over m xi, right? And at this point, it's just a matter of substituting in numbers. So we would end up with, well, what was k? K was 250 newtons per meter. And then we had 0.1 kilograms here, and we're going to multiply the whole thing by 0.04 meters because that is our spring compression, right? If we do that, we're going to find a final velocity at the point A, excuse me, of 2 meters per second. Okay, so that would be our answer for part A. In part B now, do I have space here? Maybe I'll start on the next page. In part B, we want to look at what the velocity of the car is going to be as it goes through this whole track and ends up here at the final point, FB, final point B, right? So it's important. Let's remember that we're dealing with a frictionless track here, right? So the path, basically this is path independent. It doesn't matter which of these courses we choose. We could put in a third one here. It could do whatever we want it to, as long as it ends up, oops, and it ended up too low there. But if it ends up back here at point FB, it doesn't really matter what the path was, right? Like this whole process is path independent, and so we only need to worry about the change in height here. So I'm going to rewrite this sort of general key equation here that we've generated above. Maybe I should box that a little bit. Okay, so I'm going to rewrite that one down below, and we're going to work with it again here in part B. Okay, so again, what do we have? Initially, we have some half mv squared, v initial squared. That's our initial kinetic energy. We have some mgh initial, and we have some 1/2 kx initial squared, right? And then in the end, we're going to have some 1/2 mv, and now it's going to be final b, because we're going to be considering what's happening at point B squared, plus mgh at our final point B, and again we're going to have potentially some potential spring energy, right? And that's going to be oops, that should be a B. That's going to be written like this, okay? But again, so what are we doing? We're thinking about the car starting off up against the spring over here, and it finishes over here at some point FB, right? So clearly we're not going to have any initial velocity. Again, it's up against the spring, so we can cancel that term out. And in the end, there's not going to be a spring involved. The car is just going to be rolling along the track, so we can cancel that term out. But we do have a difference in elevation here, in height, from our initial start point to our final point B. So there is going to be some difference between this term and this term, so we can't just cancel those out. There's going to be some initial spring potential energy, and there is definitely going to be some final velocity, right? Some final kinetic energy involved here. And so that's all the simplification that we can do sort of initially. Now we need to start working with the equation. Maybe I'll just rewrite it, and we can start manipulating the equation. Okay, so we have mgh initial plus 1/2 kx initial squared, and that's equal to 1/2 mv final b squared plus mgh, and these are getting too big, final b. Okay. So what I'm going to want to do here is basically I'm going to be working towards isolating this final velocity term. That's what we're really interested in, right? So I guess I can start off by moving this term over. If we do that, I can factor out an mg, right? So we're going to end up with mg h initial minus h final at b plus 1/2 kx initial squared equals 1/2 mv final at b squared. And maybe I'll skip all of the, or should I skip it? Maybe I shouldn't skip it. Let's not skip it. Let's work through it here. Okay, so if we think about this, we're ending up with our initial height minus our final height. And so what is that really? Well, that's just minus h, right? If you think about that, that's just minus h. And so we can kind of clean this up. We end up with minus mgh plus 1/2 kx initial squared is equal to 1/2 mv at final b squared. And let's just continue cleaning things up. I'm going to multiply through by 2 and divide through by an m. And so what does that give us? Let's put in some implications here. And so that ends up giving us 2gh, because I've multiplied through by 2 over m, right? Plus k over m x initial squared equals v final b squared. And so now I'm just going to take the square root of both sides. We're going to select the positive root, right, because we want a positive velocity in the end. If we do that and I move our velocity to the left-hand side, we end up with a velocity final b equal to the positive square root of k over m x initial squared minus 2gh. Okay, and at this point we just substitute in numbers. We're given k, we're given m, we're given x, we know what g is, we know what h is. So if you substitute in numbers for all those, make sure you're careful about how you do the substitution. You're going to end up, excuse me, you're going to end up finding VFB is equal to 0.69 meters per second. Okay, and so we can do a little bit of a sanity check here. We found a velocity of 0.69 meters per second here at point final B, and we found a velocity of 2 meters per second at point final A. Does that make sense? Well, it does kind of make sense, right? So the car is initially launched by this spring, and as it crosses this final A point, its velocity is 2 meters per second. It then goes through this track, and the track is frictionless, so it's not losing any kinetic energy, but it ends up higher up than it did when it started, right? It's 0.18 meters higher up than it was when it started, and so there's some energy stored as potential energy in it. So you would expect its kinetic energy to drop, i.e., its velocity to drop, and that's what we find. So we had a velocity at point final A of 2 meters per second, and at point final B we're at 0.69 meters per second. So that's great. That's what we would have expected. So now a little addition to what they did in the text here. Let's take a look at what would happen if we considered point final A as our start point. So the car is at point final A with a velocity of 2 meters per second, and point final B as our finishing point, right? So all we're doing is just looking at different snapshots of what's happening in the system, but we would expect the same results, right? If we consider what's happening with a car at point final A and what's happening at point final B, we should find that at point final A we're going to have some initial velocity 2 meters per second and some final velocity of 0.69 meters per second, right? So let's see if that's what we actually end up finding using the tools that we have here, right? So again, I'm going to go back to our original equation here. So initially we're going to have some half mvfa squared. And so remember, so this is our initial kinetic energy, and we're counting point Fa as our initial point now, right? We are going to have some initial gravitational potential energy at point Fa. I can include the spring here, but we know the spring is not going to play a part, right? Because the spring is happening before what we're sort of looking at here. But let's include it here, and we'll cancel it out afterward. And again, this is going to be equal to 1/2 the final kinetic energy that we have at final B here, plus mgh at final B, plus 1/2 kx final B squared. Okay. So as I said, there's no spring involved in the beginning here, right? Because we're thinking about point Fa as our starting point, and there's no spring involved at the end because there is no spring at point final B. So we can cross out those terms right away. we can clean this up a bunch at this point. We can see that in all cases we have this m term, right? So I'm just going to go through, cancel out those m's, and rewrite the two terms on the left and two terms on the right here. And so we're going to end up with 1/2 VFA squared plus GHFA equals 1/2 VFB squared plus GHFB. And so we can now, well, what are we interested in? We're interested in finding the velocity at the point B here. So let's isolate that. We're going to start off by moving this term over. So I'm going to do that. So what we have here is we have 1/2 VFA squared plus, I'm going to factor out a GH. We'll have F, we'll have, oh no, I shouldn't do that, oops. We're going to factor out the G, I should say. We're going to have HFA minus HFB here. And this is going to be equal to 1/2 VFB squared. Again, this is going to result in a minus h, right? Because we have our initial height and we're subtracting our final height, so we end up with a minus h. Let me scroll down a little bit here. And so we end up with an equation that looks like this. I'm going to multiply through by 2 just to clean things up a little bit, and we're going to end up with an equation that looks like this. Right, yeah, that should work. Okay. And so now it's just a matter of taking the square root, and that should be an equal sign, of taking the square root of both sides and solving. If we do that, we're going to find that our VFB, so we're taking the positive square root again, is equal to VFA squared minus 2GH. If we substitute in numbers, so for our VFA, we found that in part A, this is 2 meters per second. G is our normal G. H is our 0.18. And so if you make this substitution, maybe I'll clean this up a little bit. Excuse me. You end up with you end up finding that VFB, unsurprisingly, is equal to 0.69 meters per second, right? So this is good. This was a good double check that this equation sort of works everywhere. We expected to find the same velocity, and we did. We found the same velocities at point final B, no matter how we did this, right? So maybe the last thing to note here is for part D, and we're not actually going to do the calculation, but what if this track had some friction, right? So let's say the track had some friction. Friction is a non-conservative force, so it is path dependent. So it does matter. It does matter which one of these courses we choose, right? So we would need to figure out which course it is, and then calculate the work done by friction that's bleeding energy out of the system, and then subtract that from everything. But we're going to move on to problems like that later on. We're going to see that they're a little bit more complicated. Okay, so for part D, really my question was, could we do this if there was some friction in the track? And the answer is yes, but the calculation would be harder, and we would also be dealing with path dependence. So we would have to be worried about sort of what path this car is taking, right? So maybe I won't even include that here as a letter. I'll just include it as sort of a discussion here in the video. Okay. So just remember, we could do this with friction. We will look at problems with friction shortly here, but it would be more complicated. Okay, so we'll just leave it there for this one, and I'll see you guys in the next one.